make this thing. It's got 4 sugars, all attached to one another. And we have a thiophenol dangling off the end. Okay. Sure. How the fuck do I do this? So, first thing, whenever you're given a problem, so today what we're doing is we're just solving things. I like to do this as a group, so if anyone wants to, I'll try and give pauses for people to think about this too in the individual things, but we'll kind of do this a little bit guided so it doesn't take forever. Is what we want to do is reduce this down to the basic issues. And our basic issue is that we want, sorry, I just need to move this effing panel out of the way. We want to make this from its component sugars. And so let's say the question is, make this from any sugar. And to make this particularly challenging, we'll say they have to start deprotected. Okay. So what you want to know is, okay, so what are our challenges here? Up here, we've got a mannose. Let's call this sugar A. It's a mannose. Now, the thing to remember about mannose is we have that problem with trying to get things cis on the mannose. That was hard. But this is trans. We have an up OH. We have an alpha thing. That's going to be a relatively easy bond to make. So it doesn't need to attach to anything else. So that's good. So we have mannose up there. Okay, down here, notice we can start chopping away at the edges is probably the easiest way to do it. Oh, I did not intend to make the bond like that. Sorry. I'm going to just change, sorry, I'm going to change shit. I have exited out of this, so I can't actually delete the underlying drawing. I am deleting that. I wanted to make this anomeric. I didn't want to make that. That's much more challenging what I drew. Let's just say it's glucose. And what we have here, so we have an alpha mannose, we have a beta glucose. Again, nothing challenging. OH is everywhere except we need to make a beta bond. That's doable. We can do that with glucose. In the middle here, we have a GalNAc. It's galactose because the C4 is axial. And it's a NAC because, well, we've got a NAC there. And this is a beta GalNAc. It is beta linked at this position. And we have something attached at 4 and something attached at 3. So this is really going to be the heart of our problem, is going to be this stupid molecule. And then here we just have a beta galactose thiophenol. So I'm going to call this one C, B, D. So we've got sort of 4 sugars here. And the thing to do is not to panic. It's to think about this portion-wise. When we solve, like, that's why, you know, you have all the time in the world to look at these assignments, because this isn't fast. So we need to take these one at a time and solve these problems one at a time, and then figure out what needs to happen when we start putting things together. So let's just start with sugar D. What I need PG stands for protecting group. What I need is that. I need to have carbons 2, 4, and 6, the hydroxyl groups on those, protected, and carbon 3 free. Because if I have that, then I can make the bond to the next sugar. So that's my target. That's what I need to make. So now we need to think about how we can make that.
Okay.
Okay, so let's say I'm allowing everyone. Let's say I'm allowing everyone to start from one of the peracetylated galactoses, because we cover or sugars. So you're always going to want to start with beta. So let's say we have this molecule.
Can we begin from galactose and maybe do the protection as well, like do it today?
Uh, okay, we can start from lactose, yeah, or galactose, yeah.
Yeah,
So
galactose.
we make this in one step. Sorry, I'm gonna draw my arrows Chinese style from or Arabic style from right to left because I started on the left. Um, so we covered the chemistry of this a few classes back over this particularly.
Yeah, I just wanted to, specifically leave these carbon 4 behind. The third carbon, sorry.
Yeah, well, we'll
From
get to
this.
there. Yeah.
Okay.
Well, no, you can't actually leave that unprotected. There's no
All
good way
right.
of doing that. You're going to have to kind of play with this from here. This is your starting material for almost all sugar stuff because the anomeric position is a real pain in the ass. And so once you have something here, we can start doing some chemistry with it. But the problem is you can't protect these sugars, alcohols, in the presence of this OH. And a lot of the chemistry that we talked about, a lot of the work we did with glycosylations doesn't work if you have a lot of free alcohols because they're all nucleophiles. And so they're all going to react with all the intermediates you're going to make these activated things. So you need them protected. So you can't react. This will react first, but if this reacts first, then you have all these free OHs, which cause trouble. So normally, you almost all sugar syntheses start with protecting with acetates. It's a nice building block. So one of the ways we saw to make this, we can actually put that thiophenol in, was to take this guy and treat this with BF3 etherate. And what that does is it hydrolyzes. Well, what we're going to do is we're going to activate the acetate with the BF3 and we're going to put in the thiophenol. So we covered that back when we talked about thioethers. ethers.
Is that a squiggly line for that one OH that you circled in the bottom right?
Yeah, this is. Yeah, because
Okay.
it's a free OH.
Okay.
But the anomeric position is always squiggly, which is why it's such a pain in the ass. So this is no longer squiggly. And so we get beta here because of the anchiomeric assistance from this acetate. Is that cool? So what we've done here is we've now taken care of one of our spots. We have the right thing here. Now, we could choose to use that for glycosylation chemistry. We could activate it. We could do all sorts of stuff. But, let's just leave it as a thiophenol because that's what it is in the product. So we've got one thing done. We've taken care of that center. Now, this sequence of reactions I'm starting with. I'm starting with this one because this is a really very standard sequence of things to do. Now we're going to treat this with sodium methoxide and methanol, which is the way to cleave acetate protecting groups. If you've been on, took a look at that lecture. If you haven't looked at the protecting group lecture, you should look at the protecting group lecture. I think one of the questions in the assignment is also, here's a bunch of protecting groups. Look up how to put them on, how to take them off. So sodium methoxide methanol deprotects the acetates, free OHs. Okay, that's great. Now we got 4 free OHs. I only want 1. So this is where this kind of becomes like a game of puzzle solving. It's actually the kind of thing that I like about sugar chemistry. And it's because I'm a masochist.
So maybe we can use the benzylidines.
Okay, so let's take a look at that. So let's use a benzylidine. What reagents would you use to put on a benzylidine, Samra?
I can.
Okay, I'll just put it on. I'll just draw them here. Let's use dimethyl benzaldehyde acetal. I said that wrong. Benzaldehyde dimethyl acetal. And a little bit of catalytic acid. So you're going to do a benzylidine. So where am I going to put that benzylidine?
4 and 6.
Yeah, I agree. So I'm just going to, because sometimes phenol takes too long to draw and takes up too much space. So this circle with a line through it also means phenol. Phenol does not take up too much space. But I have no idea how this convention happened. But you will see this in older textbooks. And it's useful when you're completely out of fucking space. Okay. So now 2 and 3 are free. I completely agree. That's exactly what's going to happen. Now, I'm going to let you in on a secret and say that this is really hard to separate these two. So there is an argument. There's some papers on this. This is not the route I would suggest, but there is like the route that we took here, and because now we run into this, because the problem is now we've done that. Now we run into the problem of differentiating carbons 2 and carbon 3, which are really hard to differentiate. So, and for whatever reason, I went from galactose to glucose. Sorry. But I've seen it argued if you use a bulky this is piv chloride, pivyloyl chloride, pyridine, that this guy is more nucleophilic. The argument I've seen is it's further away from the anomeric position. I think that's a bullshit argument. So I don't quite follow why that would follow. But you do get some very slight selectivity. 3-piv about 60%, 2-piv about 40%. Where you put the piv, but well, that's inaccurate. It's more like 3-piv about 20%, 2-piv about 10%, 3,2-dipiv about 30%, 40% or so. No piv balance. That's about right. So you do get selectivity for protecting the 3 position over the 2, but there's a lot of other shit that happens. You get dipivs, you get no pivs, you have very poor selectivity in this. It exists, but it's shit. So here's a lesson. Try not to get yourself into a situation where you need to differentiate between carbons 2 and carbon 3, because you're going to be fucked. It's hard to do. So what else can we do?
Maybe go for 2 and 3 before first.
2 and 3 before?
I mean 2 and 3, like I know. I need to think first. We had acetinoids as well.
Yep. So if you treat this with the one that is not thermodynamic, the kinetic one, remember these guys like making 5-membered rings, and they like making cis 5-membered rings. And the only cis 5-membered ring in this thing is 3,4, because 2,3 would be a trans 5-membered ring. So now what we've done is we've differentiated the OH on carbon 2 and carbon 3.
Yes, makes more sense now.
Okay. So now what we'd really like to do is, do we now need to differentiate carbon 6 and carbon 2? The OH on 6 and 2, or can we protect them with the same thing?
We can protect them with the same thing, doesn't matter now. Not going to participate in the reaction.
Okay, let's protect them with the same thing. What would you like to protect them with?
Acetate?
Yeah, I like that. So we can just protect them with an acetate, acetic anhydride, pyridine. You can add a little bit of DMAP if you like. It's a catalyst. I think we've talked about DMAP. I know I've talked about DMAP. I've drawn it, but it's, if you don't add that in, that's okay. You don't need to. It'll work fine without. It's that. And what does it? Acts as a nucleophilic catalyst. It attacks the acetic anhydride. It makes it a better electrophile. Okay, so if we do that, oops, we have that. Okay. What's our next step?
Store D and maybe start working on C.
Sugar C?
Yep.
We're not done sugar D yet, though. We don't have that free 3OH.
Okay, so
I do like the
maybe
idea of this is too hard. I'm giving up on this problem. That is a very storied approach towards chemistry. But let's finish this guy off. What will we have to do?
no, actually maybe I was more like, so if we make it a nucleophile on the C3, then maybe we can attack it on the anomeric carbon of C.
Right, but we need this to be an OH.
Yep.
Right now, it's not an OH. It's an acetonide. So we need to remove that acetonide. And the way to remove acetonides is with acid and water. The problem is you can't selectively remove an acetonide.
Thank God. I thought the acetates are gonna fall off too.
No, acid and water, the acetates are stable. So, but we're not, but our problem here now is we have these two OHs.
Okay.
So I'm looking at those and going, shit, I'm not sure how to differentiate those. Now, you do have a little bit more difference here. 2 and 3 you're in trouble with because they're both equatorial. This guy is more nucleophilic. So if you dump this in and you expect this to act as a nucleophile, this guy is going to outcompete that guy. So you're going to get decent selectivity. And I would argue that it might even be worth your time to not try and protect for in this condition. But I think this might not be the best approach because now we're kind of a little stuck. So what I want to do is I want to go back to here. And Samar and I had a brief discussion, and Samar said, okay, it doesn't matter. Let's protect both 2 and 6 with the same thing. So I'm thinking, you know what? Let's not protect 2 and 6 with the same thing. Because what could happen now is, let's say I could magically have this. Suddenly I could reach back into the benzylidine. Then I'll have 4 and 6 tied up, which will only leave me with 3 free. But for that to be possible, I need to have protected 2 and 6 with different things. So let's think about this whole thing. So the next idea I want to bring into this, which is a lot of ideas here, is we want to keep track of making sure that we're using protecting groups that are compatible with one another. So we can put some things on, take some things off. And we want to make sure that we are keeping in mind that not only do the protecting groups need to be compatible within this sugar, they need to be compatible on the final sugar. So that when you put everything together, you can start making those bonds and you have compatible protecting groups with everything. On paper chemistry, my favorite compatible protecting group for these kind of things is a benzyl protecting group, BN. The reason is that it's stable to acid and base, so you generally can do anything else the rest of the molecule. And you can take it off selectively with hydrogen and palladium, which doesn't damage anything else in the molecule. Like strong acid, like over here, can cleave glycosidic bonds. So it's not ideal to use a strong acid if you already have a disaccharide bond somewhere in your molecule. So that's where hydrogen and palladium really are nice. So with that in mind, I'm just going to take this molecule, I'm going to draw it on a new page. We can selectively protect 6 easily because 6 is much less hindered than 2. We want to put something on that we can take off easily, and it needs to be relatively big, so I'm actually going to use that PIV chloride that we just saw on the previous slide. It's big and bulky, and so it's going to look for that primary, and it's not going to react with the secondary. The other nice thing about PIV is it doesn't have any acidic hydrogens. Acetate does. The problem with acid, like you can put an acetate on something, but then the problem with the acetate is that you have that down here. Is you have that. So if you were trying to stick a benzyl group on somewhere else and use sodium hydride, well, you're going to make the enolate of the acetate. And then that's going to do chemistry with your benzyl bromide, and everything's going to get to shit and stuff. So acetates are great groups if you're near the end of something, or you know you're going to be taking them off soon. But a better option for acetates are benzoyls, because again, we don't have any proton here, so we don't need to worry about at base. All we need to worry about is nucleophiles to take them off, so we can use bases. So benzoyls tend to be more general than acetates. Or PIVs, like the one we have up there, because again, that's got no hydrogen here because it's surrounded by carbons. So you do see quite a few of these for these kinds of things because they stop side reactions. So we can make this, and then I'm kind of suggesting you might want to consider this. Sodium hydride, benzoyl bromide. You're going to protect that because it's the only OH left. And that benzoyl is not going anywhere until the very end of our synthesis. We can take it off with hydrogen and palladium when we're done everything.
Sorry, you might have said it already, but why does PIV selectively like go to that OH?
Bulky. So this is a secondary OH. This is primary.
Okay.
So primary is a lot more accessible.
If you let it go for long enough, would you protect both of them?
Yeah, if you let it go for long enough and use an excess of PIV, but if you use one equivalent, like 1.1 equivalents of PIV, you don't let it go very long. Well, you can let it go as long as you want, but it'll just cap 6 first. Because you just don't have enough PIV. If you use 2 equivalents of PIV, then you would get both of them if you let it go long enough.
Gotcha.
Because we kind of have there's only real two principles here for us to differentiate things. We've got this benzylidine acetonide trick, and we've kind of looked at both of them, so I'm really glad we went down both of those routes, Samra, where we can tie up the cis 5-membered ring selectively, or we can make that 6-membered ring with 6 and 4 with the benzylidine. That's one of our tricks. The other trick we've got is we can react with the C6 first because it is less sterically hindered. So we can make this. This is actually the hardest one to get is the one. So we're actually starting with the hardest example. All the other sugars are going to make in this synthesis are going to be easier. Because I know this is a bit overwhelming. So we have this. Now what we want to do to get this guy free, again, is we're going to want to make that benzylidine between 4 and 6. But to do that, we're going to need to remove both the acetonide and the PIV group. And we can do that. We use sodium ethoxide and methanol. Which, again, removes all esters, basically. So PIV falls off. And then we can use acid and water, which removes all acetonides or benzylidines or whatever. But again, not going to touch our benzyl group, not going to touch our anomeric thiophenol. Remember, this guy, we need really specific things. We need like IDCP or we need NIS and triflic acid. It's not going to react for a bunch of weak-ass acids and weak-ass bases. So at this point, we have freed up all 3 of those OHs, and we have protected 2. So this is why carbohydrate chemistry can be a bit stupid. This is actually, I think, the most effective way to do this sequence of reactions we have done. And what we have done, if we look at it, is one from galactose, with the thiophenol on it with 4 OHs. It was 1 step to make this acetonide, a second step to put on this PIV group, a third step to put on this benzyl group, a fourth step to take off the PIV group, a fifth step to take off the acetonide. So it's taking us 5 steps to go from 4 free OHs to having a benzyl group on one of them and 3 free OHs. At every step, you're losing yield. This is a
Now
pain
do
in
we
the ass.
now do we try the benzylidine and make C3 specific?
Now we try the benzylidine and do that. Exactly.
Wow, it's beautiful and scary.
Because we've taken care of that other problem. So again, we have different. So here now, I said, don't get yourself into a situation where you need to differentiate 2 and 3. We have kept ourselves out of that situation because we have differentiated 2 or 3 already. Bonus because benzylidines can also come off with hydrogen because they are just like benzyl groups but double benzyl groups. So we can take this off with hydrogen and palladium. So we're kind of done. We have something where in one step we can remove both of these protecting groups later. It's kind of like D prime. This is ready for coupling now. This has got everything we need. We've got what we need at the anomeric position. We have freed up the single proton OH we want. So this is exactly what we want. Okay. Let's take a bit of a break. Like not because we're going to stop or anything, but because we're going to go let's look at B. So B is easy. We want beta glucose. And we're going to react it with an alcohol. So for B, we want that. We want to be able to make a beta. So what we want is a leaving group. And we want it such that when we break this bond and make the new bond, it's going to be beta. Now I'm going to draw OHs here, but of course we're not going to want OHs. We're going to want those protected. Well, okay, if I want them protected, maybe I should just write protection group. You know what, we need a shorter form.
Can we just simply use the acetate, the simple one? Like,
Yeah, so what's the advantage of acetates? Why are acetates a good idea here?
because we are going to take bases. Acetates are base sensitive, if I'm remembering correct.
Yeah.
And we might be using bases for halogenation.
What do you need the halogenation for?
To make a good leaving group.
Okay, that's one. Okay, that's fine. Any other comments on why acetates are a good idea? So I want to really
maybe for
applaud
the for the
Samra for stepping up in this class today. You're doing an amazing job, Samra. Thank you for making me not talk to myself. But you know, I okay, Paul's excusing himself by his brain not working.
actually I'm quite late in picking up the pace than other people, so maybe today's my day.
Okay. Yeah.
So okay, the acetate, yes. Maybe it is about the deprotection thing. We can easily deprotect it in the final. No, maybe we should choose another one. Maybe we should go for the benzyls.
Benzyls are good. I'm okay with acetates.
Okay, you're okay with acetate.
Yeah.
Is it because you'd have anchiomeric assistance?
Right. That's it. Anchiomeric assistance. because if we have whatever the leaving group is here, we'll make sure we get the beta bond forming because we'll have anomeric assistance. Whenever you see a beta bond, think anomeric assistance. It's your best tool for that, right? Because if you're thinking about how you make alpha or beta glycosides, we spent a lot of time talking about this. The easiest way to make the beta was to rely on anomeric assistance. The easiest way to make the alpha is to try and drive everything towards the anomeric effect. So having an ester at C2 makes this a whole lot easier. So I like clever solutions, but there's no point in being a hero. So if we start with glucose pentacetate, in one step, HBr, we make the anomeric bromide. Why mess with success? You have a nice anomeric bromide there. You know that if you treat this with a silver salt, something like silver triflate, you'll make an oxocarbenium. If you treat it with silver zero, like silver metal, it'll pull on it and you'll get sort of the chain extension will get beta attacked by SN2. But if we treat it with the silver 1 salt, we'll break that bond, we'll make the oxocarbenium, and the oxocarbenium will have anomeric assistance from the C2 acetate, which will also make things beta. So everything's going beta this way. Like this is going to make a beta glycoside. I treat this with a nucleophile, it's coming in beta. So that's a good target. Is this the only possible answer? Fuck no. You could answer this with many other things. You could have stuck benzyl protecting groups on there and put a trichloroacid imidate and then rely on using that trichloroacid imidate chemistry. You could have gone with the glycal. All those things, there's no one right answer to this. This is easy. It's not necessarily the right answer. Some of those might be higher yielding. They might be better choices. But this, you just get to so quickly, it's going to be hard to compete with. But you could get full marks doing something completely different. So that's B. Let's go to A. We'll still do C last. So A, we need an alpha mannose. Again, this is actually kind of straightforward.
The mannose.
So what do we think about as a strategy for getting that? What do we want? Because we need to protect all the alcohols because we don't want them to react. So we need protecting groups on those. And we want to end up with an alpha on a mannose.
Could we just use acetate again?
Yeah. Exactly. Perfect, Kirsten. So exactly the same argument. We have that anomeric assistance because mannose is the weird one, right? It's got the axial C2, so the acetate comes in from the top instead of from the bottom. But yeah, no, absolutely. We just do the acetate thing. So we start with mannose pentacetate. Oh, I bet you it's alpha. Treat that with HBr. And we convert it to the bromide. You could do something else if you liked. This is easy. Don't make your life harder. So that's our A prime. Again, Samra's right to think her mind on where she was like, I really want to put benzyls on here because we have benzyls on D prime, and so we're going to have benzyls in our final product. We have acetates here. They're not necessarily incompatible. It's just it would be nice if we could use one thing to deprotect everything at the end. If we need to do two things, it's not the end of the world. If we need to do sodium methoxide followed by hydrogen on palladium. But it is always worth thinking about what you've got because you want to make sure that you're compatible with stuff. Because that's going to come up now when we think about C prime, and I'm going to have to go back and look at what that is. Okay, so it's a beta GalNAc where we need carbons 3 and 4 free to do chemistry, but not at the same time. So if we think about that, we need a beta.
Sorry, John. Could you just go back to the when you added the bromide to the mannose? Is it supposed to be axial, or is it?
Yeah.
Okay. Okay.
Yeah, it does. Two reasons. One is the anomeric effect, which is why it goes axial in the first place.
Yeah.
And then you also like in the case, it's weird because look at this. You have anchiomeric assistance, but it still goes axial. Bromide is a little weird, and it's because this guy's stable and the beta is not, so it kind of displaces it to get the alpha.
Gotcha. Okay.
And here now we got anomerically stable because it's alpha and anchiomeric assistance. Like it's really good in mannose. Like it's even more likely to do it. The yields are actually about they're in the high 90s with most of the sugars for this reaction. They're about 100% with mannose. It's just really, really good. I like this reaction.
For the John, for the anchiomeric assistance for mannose, is it that the axiocarbon and it's blocking the top face? Like
Yeah, this acetate, when you make the oxocarbenium,
yeah.
this acetate floats around from the top face, blocking the top face. Yeah.
Okay. Okay. Thank
So
you.
it does the opposite of all the other ones, which block the bottom face. It's a pain in the ass to make beta mannoses, and we talked about a few ways of doing it. But that's really hard to do.
So that was lecture 7.
Yeah. It was somewhere back there. But what we really want kind of is we want to make one of these first. So we kind of want one of these be an OH at a time. And the other thing we need to concern ourselves with is whatever this protecting group is. So what we effectively want is either with that guy protected. It doesn't really matter which one. I think we can think about which one's easier to make, which is always the way to think about these. We want either one of those, and we need to do something at that anomeric position. So I'm actually just going to write this as...
So we actually want an alpha, right?
Yeah, do we? I think it's
Yeah,
beta. I
because
think it's beta.
um
Yeah, it's beta here.
we okay.
It's going to be beta here. Alpha would have been tougher, so I picked beta on purpose. Alpha's tougher because you have anchiomeric assistance from this NAC. So beta is easy to make with the NAC present.
Okay, so that is an ESA.
Yeah, you can use an azide and you can get alpha and then switch it after you make the bond, then take the azide to the NAC. That's how you make the alphas. We're actually doing that right now in the group. Mike's doing a lot of that. So this is what we want. I'm just putting X here where we can figure out what we want X to be. It can be anything. So we want this. And now let's just keep, so I'm going to make the level of difficulty a little bit easier by having an NAC there, but I'm going to raise level of difficulty because let's start from galactose pentacetate. So you actually wouldn't start from galactose pentacetate, and this actually would start from glucose pentacetate to make the galactose, but we're not going to cover that chemistry. It's just a little weird. It's a fine detail that this just one of these reactions doesn't work very well with galactose, and I have no idea why. So we don't need to care about that. Okay, so we got galactose pentacetate. We want to turn it into one of these two things. Go. So last, I don't know. So last lecture, it was a quiet lecture. I think it was just Samra, Kirsten, and Susanna, or maybe it was just Susanna and Kirsten. It was a quiet lecture. We talked about amino sugars and deoxy sugars. And so one of the best ways to introduce this amine is from, there's multiple ways to do it. We saw 3 kind of different good ways to do it. One is from the glycal through azidonitration. One is from displacement of an azide onto an iodide or some other leaving group. And the third one was reductive amination of a ketone. So you treat a ketone with an amine, you reduce it, which makes an imine, like carbon nitrogen double bond. You reduce that down to the carbon amine. All those will work, but since it's at the 2 position, the glycal makes sense. And the other really nice thing about a glycal is that suddenly it takes some of your oxygens out of the way. So if we're thinking about this, I want to make this into a glycal. Anyone remember how to do this?
We can do the selenium one. Oh, but that would be it would be, but it would make a quick, right? We can easily do the azidonitration alongside. We use the selenium diammonium, I guess, nitrate.
And ceracomonium nitrate?
Yeah,
Cerium, not selenium, right?
sorry. Yeah.
Yeah, exactly. That will take us forward, but how do we get here from here? Okay, so just as a refresher, good way to do this is let's put the bromide in. All good. Then we can treat this with zinc metal. And this gives us the glycal. Now we've actually kind of made our problem a little bit easier for ourselves, because now we're coming back to this protecting group issue with these other sugars. And we've removed C2 altogether. We could put C2 back in now, or we could wait. There's no rush. We could actually mess with all these OHs, get what we want. We can even attach the other sugars before we deal with this glycal. So remembering that these were our goals, it doesn't tell us what order we need to do things in. You can think about that. Now, it's perfectly fine. You can go ahead and install this if you like. Nothing wrong with that. Absolutely nothing wrong with that. But I think it's actually somewhat easier to think of the fact that what you've just done is you've gotten rid of one of these pesky OHs. And the C2, C3 division of labor thing is hard enough to do on the best of times. So just getting rid of C2 altogether does make life a little bit easier. Because now C3 is pretty different.
So maybe we remove the acetates.
I like that. How do we remove the acetates?
With the base.
Okay, what's your
They're
base?
base sensitive. No, not. I don't remember the base.
Let's use sodium methoxide and methanol. Nucleophile more than a base, really. Basic nucleophile. Okay. Acetate's gone. OH is left. Okay, now what do we want to do?
Now we want to protect them selectively.
Perfect.
Go for
Great. We
the
want to protect them selectively.
I guess I meant the C4 and the C6, right?
Okay, so what we'll do is we'll target this guy, right? With this free OH.
Yep.
Yeah, so we can protect C4 and C6 with the benzylidine.
Yep.
You know, and this is, I completely understand this is hard. This is probably some of the hardest chemistry you've looked at and seen strategically, because we're not going into the depths of mechanism here. We've covered all that. But it's just thinking about how you put these things together. But there's actually very few limited ways of doing this. So we're seeing the same patterns over and over again. I want to protect I want C3 free. I'm going to protect 4 and 6. If I want to protect 4 and 6 together, I'm going to use a benzylidine. I really don't have a lot of options. So we do that. So we get that. Okay. Now what do we want to do? You know what? I'm going to help us out with what we want to do by calling this, I can't remember, I think this is B. B prime. So now, no, next slide. If I remember right, we've got,
It's A, but sorry.
oh, that middle one's A?
Or sorry,
B.
never mind. Never
No,
mind. I'm an
we
idiot.
want to go for the B. We attach.
So let's
We are
just
doing
remember what
C.
we got here. We've got this guy. We've got, sorry, also an alpha bromide, but it's got the C2. And we've got the one that we struggled mightily to make.
Okay.
I can't remember if this one was a galactose or it was a galactose. There's a lot of galactoses here. That's actually probably true. This is I didn't make a specific sugar, but this has a very, very typical core on it. I've kind of inverted it actually. Normally it's galactose, galnac with the galnac attached to other things. Here we have galnac galactose, but still very, very typical core of bioactive sugars. So I'm sure this is on something. So we have those guys, and we have our glycal. So we're actually in a position to start snapping things together. So we want, I think it was a glucose over here, right?
It was C was galactose.
Yeah,
Glucose.
that was the
A is mannose, B is glucose.
and D is galactose.
Yeah.
Yeah, so this is a glucose, and this is, we wanted the glucose here attached to this guy. We have the OH. We got the glucose building block. Let's attach those together. So what would you use to do that? An anomeric bromide. We want to go through an oxocarbenium. There's no reason not to, because we'll get anchomeric assistance. So let's use silver nitrate. Now we can think about what solvent we want to use. We want to bias to make the beta, but again, we could play with the solvent, but it's not going to matter because we've got a freaking C2 acetate. It's going to do anchomeric assistance. If we didn't want anchomeric assistance, we shouldn't have put a C2 acetate there, but we do. So whatever solvent we use doesn't freaking matter. So pick whatever solvent you like. As long as it's a solvent with no nucleophiles. If you try and do this in ethanol, it's going to be a fucking disaster. So like dichloromethane. Silver nitrate, dichloromethane, magic. We have just made our first glycosidic bond. So we couple two of them together. Okay. So put a nice big check mark next to that and feel like we've done something, accomplished something. Okay, so now what we need to do, well, we have options. You can install the azide, the NAC, if you like, or we can attach A prime, the mannose. Either one is perfectly fine.
Let's attach. Oh no, let's attach mannose first then.
Okay, let's attach mannose first. Okay, so what do we need to do that?
Deprotect benzidine, and how do we do that?
Yeah. So we actually, when I was doing a benzidine lecture, or the protecting group lecture, the one cool thing about benzidines at the C4 and C6 position is you can selectively open them. So one thing we could do is you could rip off that benzidine altogether. Fine. Get rid of the whole damn thing. Got to be a little careful with condition. Acid will do it just fine. No problem. I was thinking you have to be careful because you can't use hydrogen because you'll react with this double bond down here. So you can't use hydrogen on palladium because I'll react with the double bond first. But yeah, we could use acid and water. That's fine. But we could also open it such that the benzidine turns into a benzyl group on C6, leaving OH free, C4OH free. And that's the easier way of doing this. So if we use a bulky base or bulky acid, so if you remember, BF3 is a Lewis acid, I can use a bulkier boron. I'd accept BF3, but this is like the same thing, except it's got two butyl groups. So it's a big, bulky boron thing. And it's going to attach to this guy because that is much less hindered. Sorry, I want this guy open, not that guy. Ignore me. I always do this, and then I make the mistake, and then I have to erase it because it's like that logic's not going to work. Just going to use acid and sodium cyanoborohydride. So if those who haven't looked at that lecture in a little bit, you're going to protonate this guy. It's a small proton. It can go to the more hindered alcohol. And then you're going to deliver a hydride from sodium cyanoborohydride, which is a pathetic hydride source, to that carbon. And then it's going to choose which of these OHs will leave. Well, that's going to be an OH. That's not. So you're going to break that bond. So you're going to end up with I'm just going to call this B over here. I'm not going to, or C, I guess. It's the right thing. We don't need to draw it out every time. And we have a benzyl on C6 and C4 free. Now, you could have taken a benzylidine off completely, stuck something on C6. That's fine. That's fully doable. In the lab, I've definitely done both because sometimes this doesn't work as well as claimed. But on paper, it's beautiful. Okay, so if we want to attach that to A, what do I do? Oh, we just did it.
Yeah, is it not the same as just using the silver?
Yeah, these aren't trick questions.
Okay, cool.
Not trying to fuck with you guys. Like this isn't trying to be more complicated than it needs to be. Yeah. Like the hard part is thinking about the protecting group strategy, but the actual snapping things together, we've been talking about that ad nauseum in my mind. So we've made all those bonds now. So we've now actually attached 3 of the sugars together. All we have left to do is attach the 4th one. And Samro is right. We can install what we need to here using ceric ammonium nitrate and sodium azide. If you need to look that up, that was in last lecture. So we've installed the azide. This guy's a really good, it looks like it should be a good leaving group, the nitrate. Like looks like it should be something you can activate. It's really a pain in the ass to work with. So what we almost always do is this is almost in brackets. And you treat this with a bit of acid and water. And the damn thing hydrolyzes off. No, not AC. It's just A. Sorry, it's turning slowly from A into an acetate. Now, we want this to be beta. We're going to make a beta to this guy here. So we could try and do the chemistry directly at this point, convert this into something and do this with the azide present. But since we want it to be beta, it makes sense to take care of antiomeric assistance. Why not? Never Never make your life harder than it needs to be. So we want to reduce the azide to the amine or the NAC without touching anything else. So again, last class talked about 3 different ways to reduce the azide. We can use hydrogen on palladium. Now, you don't need a lot of hydrogen, you don't need pressure, so it is compatible with the benzyl group. The benzyl group will not come off under the hydrogen pressures you need to remove nitrogen. So benzyl, you normally need like 10 atmospheres of pressure. You actually, you do need to put into a pressure vessel. The azide you can just do under a hydrogen balloon, it's fine. We can use...
Thioacetate?
Yeah, if we use thioacetate, we take it directly to the NAC, which is
Yes.
nice. So in one step, you go from azide to NAC using thioacetate. Or you could use the Staudinger reduction, like the triphenylphosphine. There's lots of other ways to do it. This is just 3 examples I'm giving. You can provide something else. If it works, you get the marks.
John, I have just a quick question here. So if you have the amino group, what could be the most suitable way to go towards the acetate?
From an amino to an acetate?
Yeah, if in this situation.
So if you had the amino group, then the best way to do that is probably acetic anhydride and triethylamine.
Okay.
It's just like acetylene and OH. For whatever reason, pyridine doesn't work very well. I don't really understand why. Well, no, I do. It's because an amine is more basic than pyridine, so that amine isn't going to sit as an amine. It's going to sit as an ammonium and an H3 plus, and it's not going to react. So you do need an amine base. So triethylamine is a good base.
Thank
But
you.
but I'm not. That's a detail. I don't care. Just acetic anhydride base done. I'll give you the marks. Okay. Now, OH is not a leaving group, so we need to do something with that anomeric position.
We need to make it alpha.
Yeah, you can. You've got antichimeric assistance, so you're going to get you're going to have a beta product. The product is beta. We go back. I think the product's beta. I hope so. I meant it to be beta. God, we've drawn a lot of stuff. Yeah, it's beta. So it doesn't really matter what orientation that the activating group is, because we're having antichimeric assistance from the NAC. So the leaving group can be alpha, the leaving group can be beta. Once it's an oxocarbenium, it doesn't matter. So we just need to turn that into a leaving group, the OH. So we see a bunch of different ones. The one that started with an OH was the trichloroacidimidate. You had to have an OH there. And then you turned it into a trichloroacidimidate. But we also saw how it turned these into aryl fluorides. You could acetylate that, really easy, acetic anhydride, and then you could turn it into an anomeric bromide if you like, or into an anomeric thioether. You've got all the options that you want in here, but let's just do a TCA for shits and giggles. Sodium hydride, trichloroacetonitrile, and this is the thermodynamic kinetic base, but gives you the thermodynamic product, so you get the thermodynamic TCA. Now, I'd be a little, in reality, I'd be a little nervous about making a TCA with this, with acetate protecting groups on things. It does work because you use one equivalent of sodium hydride, and the most acidic proton by far in this molecule is this OH. So it does work. You can do this with the acetates. I'm just always a little nervous. I just don't like doing strong bases with acetates. So what I would probably do is if I was doing this in a lab, I would probably acetylate and I would turn into the thioether. I like thioethers. That's my bias as a carbohydrate chemist. Just I really like the thioethers because they behave themselves really well. But any of them work. No, there's no wrong answer here. And if you keep going back to the same pool, if you really like TCAs because you're like, hey, this is cool, I can control everything with them, and you try and use TCAs for everything, that's fine. That is absolutely fine. There's nothing wrong with that, using that as the answer, using a TCA for absolutely every coupling. I don't think there's any of the others you can use for every coupling, but there's some that are going to be easier for some couplings or others to get to and kind of draw. And that's entirely, it's up to you. I expect if we had a question like this, I would expect 5 different answers from you guys. You'd all come up with slightly different ways of doing this one. So we have this. We have 3 of the sugars all attached together. We're set up to do the final reaction. We've got the final compound here. All we need to do is make this leave. Now, if you remember with TCAs, we have options of 2 different Lewis acids that we spent a lot of time talking about. BF3 etherate was the rip it all off Lewis acid. TMS triflate was the softly weaken the bond so you get an SN2-like mechanism. So BF3 etherate led us to an oxocarbenium. TMS triflate led us through a SN2-like intermediate. The nice thing is here, we don't give a shit which way we go. Either way, we win. If we do an SN2, I want beta anyways. Great. If we make an oxocarbenium, I've got anchiomeric resistance, I'm going to get beta. So everything here is leading you towards beta. You've kind of set yourself up for success. It doesn't really matter what mechanism occurs, you're going to get the beta glycoside. So I'm just going to rip that thing off because I feel violent right now. Next page. So we're going to rip that off. We're going to make the oxocarbenium. This guy's blocking the by anchiomeric assistance. We add in our hard-fought guy here, benzylidine, nucleophilic attack, top face, because of anchiomeric assistance. And we have, draw this a little bit lower down because I'm going to draw the whole goddamn molecule. The protected form of this guy. So what do we got? We got a benzyl here. We've got a NAC here. This is a glucose, acetate protecting groups. this is a mannose with acetate protecting groups. So we've gotten there. All that's left to do now is take off the protecting groups.
So maybe we first do the hydrogen platinum and benzyl, and the benzylidine comes off.
I like that. Yep. Hydrogen, palladium, pressure. Yeah, these two tricky benzyls will need a little bit of pressure to help them off. It's not going to touch anything else in this molecule, but it's going to rip off all of those guys.
And then we do the sodium methyl for the
Yep.
acetate.
And the most beautiful word in the English language. So you'll fully deprotected the sugar. So this I would rate as about the most difficult kind of question I could ask. I could fiddle around with it, and we could fiddle around with all the parts. You know, maybe make the mannose, make it a beta mannose, and then you have to think a little bit harder about it, or something like that. But we're not fundamentally. This is all the pieces that we need to think about when you're trying to approach one of these problems. When you're looking at these, what you need to do is you need to figure out, okay, I need to keep a whole bunch of stuff in mind at the same time. But you can always go back and rework stuff if it's not working. That's what's important. One is, and this is really important, these protecting groups all need to be compatible with one another where we're at. So you can't suddenly rely on a step where, you know, you need to free up this OH here and it was acetate protected when you've already attached these other sugars over here and they're acetate protected, because then you have to take off all those acetates at once. Can't magically just remove this acetate. So you need to keep that in mind, that if you put a protecting group on, it's ideal if it stays on there till the end. And if you are going to have to take it off, you're going to need to think about when you're taking it off and what other protecting groups are present. We didn't run into that problem because we wisely avoided it, but it would have been easy enough to run into that problem when we were trying to make both of these bonds at the same time. So second thing you have to think about then is, for each individual sugar, which OH do you want to be free, and in what order do you want them to be free if more than one needs to be free to do an attack. We ran into that problem where we need more than one here. And so, again, the big priority there is don't force yourself into a situation where you need to differentiate between carbons 2 and carbon 3, with both those being OHs. And really, the only two ways to get around that problem is if it's galactose or talose with that axial C4, you can make that benzylidine between 4 and 3, which frees up 2, that separates it. Or you can get rid of the OH at 2 and make a glycal. And if that's a glycal, then you've separated 2 and 3. Then you can do something with 3, and you can reinstall the oxygen of carbon 2 later. So what you want to do is and we had that 4,6 benzylidine thing, and then you can ring open that selectively. So really, it seems like there's an awful lot of things to be done there, but there aren't. There's very limited options to differentiate those hydroxyl groups. So you need to think about the strategy you need to get the right hydroxyl groups open. Then you need to think about what order you want to put these things in. So we were pretty smart with how we went about doing this kind of chemistry. Because what you want to make sure you don't run into a problem was, if we had put a thioether ether here, up here to start with here, instead of TCA, then we would have run into the problem of, oh shit, I'm trying to do a reaction with another thioether ether. So I got 2 thioethers ethers, and I want to activate one and not the other, and that's just not possible. Now, the nice thing about thioethers ethers is we have that option to take one of them and make it a sulfoxide or a sulfone, which were more reactive. So I could have turned one into a sulfoxide or sulfone, leave the other one as a thioether ether. Then I can activate one in the presence of the other. And so I'm a big fan of thioethers ethers for that reason. Because if I'm ever stuck trying to stick 2 sugars together and they both have thioethers ethers, I can solve that problem by just making one of them a sulfoxide. Problem solved. I don't need to fuck around with trying to modify other things. I can do it at the last minute, oxidize it up. I'm good. And the last thing to always worry about is the anomeric configuration at each of the centers. So we spent most of this course to date talking about that. So I was slightly disappointed that was actually the thing that had the least feedback from the class on things, was how to go about doing that, because that's all we've been fucking talking about. But if you, sorry, Manos. So it's really easy to draw sugars wrong. I have a colleague in Paris who on Twitter constantly corrects people's sugar structures in the literature. And so this morning, last night, I said, hey, Seb, I'm going to do something stupid. I'm going to send you this review article I wrote 3 years ago with like 70 figures in it, all sugars. And can you go through and find all my errors? And he went, sure. Like I was joking. And he said, no, send it to me. So I sent it to him. He emailed me back this morning. He said, well, it looks good, but I found an error in your first figure. No, fuck. So this still happens. So yeah, drawing the wrong sugar happens all the time. But what you just want to make sure you're doing with these is worrying about the configuration at these centers. So if we're going to make a beta, we want to take advantage of antiomeric assistance. In this case, everything was beta, so that was easy, except for the alpha, which was also antiomeric assistance. But if you're going to make it alpha, then you need to take that into consideration with what your protecting groups are, so you can take advantage of the anomeric effect and not antiomeric assistance. So these are all things that you need to be thinking about. You need to think about all these simultaneously when you're doing this. And this is the reason I'm not doing this exam as a closed book, do it live. Like, there are questions like this I know on assignment 3. Take your time, go through them now. I want you to think about these kinds of problems. I want you to think about how these solutions are. It's a really rewarding feeling when you solve it and you get something that works. You guys are all going to come up with different solutions. I'm pretty excited to see what you guys do. Okay, any question? I think this example is really good because we cover an awful lot of bases. Any questions about it, though?
I just had a small one about the last steps. Is hydrogen on palladium for taking off the benzyl groups?
Yeah.
Okay.
Yeah.
And then the methanol is for the acetyl groups.
Yeah,
well?
sodium methoxide methanol is for the acetyl groups.
Okay.
John, my question is not related to the problem, but when you covered the protecting group lecture, at the end of it, you had said that there would be a follow-up with that. I was just
I decided
wondering
not to follow up because I was going to talk about some boron stuff. I just decided to drop it.
All right. Okay.
Yeah. So this is kind of the follow-up with talking about some of the protecting stuff.
All right. Makes
Yeah, I was going to talk about some of the boron chemistry, but then I just thought more about it and went, well, we can cover it. It gives you another way to differentiate 3 and 4, basically. But we have a way of doing it, so it would just be more stuff. And I was just thinking, is there value to just throwing extra stuff on here? And it's like, this isn't comprehensive carbohydrate chemistry, of course. This is like an introductory graduate level, senior undergraduate class. If I ever teach carbohydrate chemistry carbohydrate chemistry 2, then it would be in there. But okay. So this is also where the material for the midterm ends. So next class, we're going to be talking about some C-glycosides and carbosugars, I believe. That's not going to be on the midterm. So any question that involves, I'm going to basically say which questions from the assignments are on the midterm, and I'll post that tomorrow. Do it tomorrow morning. Okay. I've got nothing more. There's no more questions.
John, does the lecture also happens on the midterm exam? Like on the day we have lecture and midterm exam as well, like both goes?
Oh no, I'm not doing that to you. There's no lecture that day.
All right.
No,
Makes
you get to write the midterm.
All right. Thank you.
How long do we agree for the midterm? 2 hours? 2.5?
I remember actually I haven't covered the last part of lecture 10. So maybe that's where you guys discussed the
Does anyone
midterm.
remember?
I can't remember either.
Okay, you know what?
I-
I'll give you 3 hours. I'm going to write an hour and a half midterm.
Can we negotiate for 4 hours?
If you need extra time, you're fucked. Like,
Uh,
I'm going to give you 3 hours. I'm going to write an hour and a half midterm, but you should have answered these questions in advance. And so it should take you about how fast can you write and think and go, oh shit, when I'm writing, I'm going, I didn't quite get this. So I might be getting the answers back in 20 minutes. I don't know.
okay.
It wouldn't surprise me. Okay.
Yep.
I'll give you 3 hours. Just in case you haven't done the assignments ahead of time. So what I'm saying is do the assignments before next Thursday.
Wink, wink.
Okay. Like I'm okay with, you guys talking with each other about them. I'm not a big fan of you guys working directly together to get the same answers. So if you need direction from each other, go ahead. But I'm very happy to talk if you guys have. No one's approached me about any questions on any of the assignments. So if anyone wants to, I'm happy to talk about that. I do have a 24-hour blackout where I don't talk about course material 24 hours before the midterm. So if you have questions, make sure you get them to me before Wednesday 2:30, and I'll be able to answer them. But it'll just point you in the right direction. Again, I can't give you the answers to this because this is the evaluation for the course. But I can make sure that you're not stuck. And I'm happy to kind of arrange office hours if anyone wants to talk. Or maybe we can do it Tuesday after class. I can just stay on and we can just chat for a bit.
That would actually be really
Yeah.
great and helpful.
Yeah.
Okay, let's do that. If anyone has questions, then save them up for them.
Okay, sweet.
Okay.
Thanks, John.
Great, thank you.
Thank you very much.
Thank you.
Good luck.
It was
Happy problem solving.
it was a fun class. Loved it. Bye, everyone.
Bye.
Thank you.